Okay, thank you. Thank you, the organizers, for inviting me, particularly Professor Hilda. So I'm going to talk about how to predict the dynamical process in networks by using machine learning. So basically, I will explain some ideas about dynamical process in networks. Then I will show how to perform the inference of network, but to understand, for instance, how the properties of network influence a given dynamical process. I will talk about synchronization and epidemic spreading. Then I will show how to predict the dynamical process by using only the network structure. And then I will discuss some challenging in this area. So a network basically is a graph which represents the structure of a complex system. So in a network, we have a set of nodes connected by edges. Then we can use this representation in many different areas. For instance, we can use complex networks to represent the web, or society, ecological interactions, so different complex systems. And you can say that this theory basically started 20 years ago, more or less, with these two papers, one published in Nature and one published in Science. And since then, networks have been applied in different areas. For instance, you can study Facebook, internet, proteins, airports, web, scientific collaboration, and many types of networks. So basically, to study networks, we have three different fields. So we can be interested in study the structure of networks. In this case, what you want to do is to describe the network structure. So what we do is to develop new measures to describe the network structure, like centrality, community organization. We are also interested in dynamics. For instance, you want to understand how the structure of a network influences a given dynamical process like synchronization and epidemic spreading. And we are also interested in applications. In this case, for instance, you want to apply network theory in medicine, in biology, ecology, engineering, in different fields. Okay? To describe the network structure, we can see here a network. And if you take a look just in the network, we cannot extract any useful information. But if you extract some measures of networks, like the average degree, number of nodes, typical distance, clustering, and several other ones, then we can get a very useful information, and then we can understand how the network is organized. Okay? In the case of dynamical process, we can have the different dynamical process in which you simulate in a network, like, for instance, synchronization. We can simulate epidemic spreading, rumor spreading, failures and attacks. So we have many different processes which you can simulate and analyze in networks. And today I'm going to talk about synchronization and epidemic spreading. Synchronization is a very general dynamical process which you can model, for instance, lasers and power grids and neurons in your brain. So it's a very, very powerful dynamical process. And one particularly important model we consider is the Kuramoto model. The Kuramoto model basically is a model in which you have the evolution of the phase of oscillator I depends on its natural frequency and also depends on the interaction with the neighbors. For instance, here you have the terms of adjacency matrix, which is 1 if you have a connection between I and J, and 0 otherwise. And the interaction is given by the coupling, which defines the strength of connection, and also the sign of the difference between the phases. So if you calculate the order parameter for this model, we can see that after a given threshold, a given critical strength, we have the emergence of synchronization. And by solving this equation by using mean field, for instance, we can show that this critical threshold depends on the network structure. It depends on the average degree and also depends on the second moment of the degree distribution. So if you have a network which is more heterogeneous, then this parameter is smaller, okay? Particularly for scale-free network, we have that the second moment of the degree distribution will diverge. Then these networks are very easy to synchronize, okay? So since this critical coupling is very small, scale-free networks are easier to synchronize than random network. This is more or less the review in Kuramoto model. If you are interested in study Kuramoto models, it was published in 2016 in Physical Reports. And another important dynamical process which I will consider today is the epidemic spreading. Epidemic spreading, you can model, for instance, the propagation of virus, bacteria, and also ideas, okay? So just to make a comparison here we have the evolution of the bubonic plague in Europe. We can see that to go from the south of Greece to Sweden and Norway, it took about 4 years, so it was a very slow process, okay? If you compare today with the pandemic flu in 2009, we can see that to go from Mexico to all the other continents, it took only 3 months, okay? So the difference here we have is that the network is very different. For instance, in the Middle Age, people could not move very far from their home, and today you can go from here to China in just 1 day. So this is the big difference is the network structure. To model epidemic spreading, we have 3 different states. For instance, of course, that can have more, but in our case, just 3. We have that individual is susceptible, so is a health subject. This individual will become infected with a given probability, will become sick. And then this individual can become recovered, so you have the SIS model, or this individual can become removed, so the individual will be immunized, so you get immunization, okay? Oops. So following these 3 states, you can have different models. For instance, here you have different models, so a susceptible individual with a given probability or rate will become infected, and then will become recovered. To solve this model, we have different approaches like mean field, quotient mean field, pair approximation. So we have different approaches. In the case of degree-based mean field, the idea is to write this equation. Then you can solve this equation by using first-order approximation. By solving this new equation is very easy. So you can get the characteristic time. Since this characteristic time must be larger than 0, then you can calculate the critical rate for the epidemic spreading. So you have the propagation of the epidemics only after this critical rate. So for instance, it depends also on the average degree and also on the second moment of the degree distribution. So again, scale-free networks, it's easier to propagate a disease in a scale-free network than in a random network. We can also model rumor spreading. In rumor spreading, we have individual is ignorant. This ignorant individual will become a spreader. So the individual will receive the information with a given probability, and then the individual can become a stiffer. A stiffer is an individual that knows the information but is not interested in the propagation. Okay. So again, we can model this by using a set of differential equations. And here, the difference between rumor spreading and epidemic spreading is that here we need a contact to become a recovered node. So, okay, so in the case of epidemic spreading, we don't need the contact. It's a spontaneous process. But here, we need the contact. This is our last review about epidemic spreading, published in 2018. So in this review, we describe the main models of epidemics and rumor spreading in single-layer and multi-layer networks, and we also provide the computational algorithms to simulate this process, okay? So the big issue is how to predict a dynamical process from the network structure. The main motivation is if you can understand how the structure of the network influences a given dynamical process, then we can change the network to change the dynamical process. Then we can control the evolution of the dynamical process by just changing the connections inside the network, okay? So for instance, you can control the synchronization in a power grid just by performing some kind of rewiring, okay? So this is the main motivation, is to understand. If you can understand exactly how the structure influences a given dynamical process, then if you change the structure, we can predict how the dynamical process will change, okay? So there are several approaches you can try to solve this problem by using, for instance, mean field approximation and different Markov chain modeling. So we have different approaches. But today, I will consider a new approach that we have developed, which is based on machine learning, okay? So machine learning is a part of data science. So in data science, what you have is input data, then you have some pre-processing, for instance, to remove some kind of noisy or seasonal effects, for instance. Then we have the data mining in which machine learning is included, and then you can perform some classification, prediction, forecasting, clustering, so you have different methods. Then you can perform some post-processing to try to understand what's happening in the process, and then you can get the useful information, okay? So basically, in machine learning, in supervised learning, we have the following ingredients. So you need the data, so you need a set of observations in which you have the input and the output in order to give these examples to our method. We have our hypothesis spaces, so you need to define the possible functions that will be associated to my process in order to perform the prediction. And we also need the goodness metric. So you need a metric to say how good is the prediction and how to adjust the method, okay? So to perform supervised learning, we need to divide our data sets in two data sets. So in one data set, you use it to train our model. So for instance, these are the examples. These examples will be provided to the learning model. So this model will learn about the data, the relation between the variables. And then we have a testing set. This testing set will be given to the learning model, and then we can try to predict. So you can evaluate how good is the prediction by using this testing set, okay? There are many methods to perform this task. For instance, you have support vector machine, naive-Bayes, neural networks, random forest. So particularly in the case of neural networks, what you have is a set of neurons that are connected by synapses. This set of neurons are defined in order to have a set of input neurons. The set of input neurons, the number of neurons will be the same as the number of variables we have. Then we perform a process in which you have the data is transmitted from one layer to another layer, and then we compare with our example, and then we try to adjust the weights in order to minimize the error. So we use a kind of optimization by using gradient descendant, for instance, in order to adjust the weights such that our prediction will be the most accurate as possible. Another important method is the random forest. In the random forest, we have our data set, then we perform a kind of sampling called bagging. By using bagging, we define several observations. These observations, each observation will result in a given decision tree. Then we combine, 100 decision trees, for instance. And by combining these decision trees, we can get our result. For instance, in classification problem, we will use the majority of the classification, for instance. And in regression, you use the average. So you combine the decision trees in order to get the result. Machine learning has been applied in physics. So for instance, this is an important review was published this year in physical reports. So you can see that machine learning can be used in many physical applications. For instance, this is a paper published in Nature Physics in which people discuss how machine learning will be important to use in physics, because machine learning is typically used in computer science and data science, but in physics, people are using, for about 5 years only. And here's another paper published in 2017 in which people say that machine learning will be very popular in physics as numerical methods. So for instance, today, if you are studying many physical processes, you use numerical simulation, machine learning will be more or less similar in the next coming years. And also in nonlinear dynamics. For instance, this is a paper published by a group of Professor Ott in Physical Review Letters, in which they try to predict chaos by using a type of neural network. They use a reservoir computer with a kind of neural network to predict chaos. So we can see that machine learning is becoming more and more important in physics, nonlinear dynamics, and many other areas, okay? So in networks, what you have is the ideas of using machine learning can be, for instance, to try to extract patterns of connections inside the graph, to study just its structure, okay? For instance, in this paper published in 2007 in Advances in Physics, maybe it's the first paper that have used machine learning to study networks. In this paper, we proposed a method to classify networks according to a set of models, okay? Later, we published 2 other papers in EPL. The first one, we tried to identify regular regions inside the network by using different methods on machine learning and statistics. And the next one, we tried to identify the outliers in networks, and these, for instance, are the most common outliers we can find in different real-world networks, okay? So, but, okay, we can use machine learning to study the structure, but one question is, how to combine machine learning to study structure and dynamics, okay? So our hypothesis is, given that we have a dynamical process, we have a network structure, then the evolution of this dynamical process will be a function of the network structure. This is the basic idea. Then if you give some examples of our dynamical process and network structure to a machine learning model, the idea is try to predict this dynamical process, okay? To perform the prediction, we have 2 different approaches. One approach is inference, and another approach is prediction. In the case of inference, what we wanted to do is to explain the data we have. So for instance, we wanted to verify how some network properties, like for instance, the network measures influences a given dynamical process. This is the basic idea. So we wanted to understand how the variables are related. In the case of prediction, we wanted to predict based on the data we have. We are not interested in understand how the variables are related. We wanted to predict only. So you have a kind of black box in which you put some properties of the network, and then we have the output. So you have 2 different approaches. The first one, we can try to understand the relation between the variables. In the second one, we are more interested in prediction, okay? So our features will be network measures, okay? So you have a network, then we structure a set of measures. This will be the set of attributes. We considered, for instance, several 10 measures to describe network structure, like average search information, which is related to navigation. Number of articulation points is related to resilience of network, second moment of degree distribution. So I have several different measures to describe the network structure. Then, in the case of inference, we assume that our dynamical process, for instance, the order parameter in the Kuramoto model, is a function of the structure of the network, okay? So you have, for instance, a regression model. Then what you do is to assume that this, we perform a logit transformation because the order parameter is limited between 0 and 1. And then we have this regression model, which depends on different network properties, like distance, assortativity, average search information. And then we evaluated this model by using Bayesian regression, and then you can quantify which measures are significant for the dynamical process, for synchronization, and also the importance of each one. And we verified that the average shortest path is the most important network property related to synchronization. So for instance, if you want to increase the synchronization, we have to decrease the distance, the typical distance in the network. So by just adjusting the distance, we can control the synchronization. Of course, that other measures are also important, but this is the most important one. We also applied this approach to epidemic spreading and rumor spreading. In this case, our output variable is the fraction of infected nodes or the fraction of informed nodes in the rumor spreading. Again, we assume a linear regression model. But in this case, we have considered a beta regression model because the beta distribution is limited between 0 and 1. Then we can write the regression equations, and then you can perform the inference, and we verified that the average search information, which is related to network navigation. So basically, the idea is to go from vertex U to V, this will give the average number of questions I have, for instance, yes or no, to go from U to arrive in V following a random walk. This is the measure. Another important one is the number of articulation points and also the assortativity for disease spreading. For rumor spreading, again, the average search information is the most important one, but also the second moment of the distribution and efficiency and the clustering coefficient. It's interesting to see that the clustering coefficient here is important, but for epidemic spreading, it's not so important. Okay, it's very close to 0. Because, for instance, in rumor spreading, we have the interaction between informed nodes will give a new recovered, it's a Stifler node, then we have that the clustering is important, okay? Okay, so this is inference, but we are also interested in prediction. In prediction, the idea is more or less the same, but in prediction, we have some limitations. For instance, what we wanted to do here, instead of perform the inference in the whole network, we wanted to predict the evolution of each node, okay? A dynamic variable associated to each node in the network. So again, we assume that the dynamical process is a function of network structure. As dynamic variable, we assume to be the fraction of infected node when the disease starts in node I. For instance, given that I am infected, how many people will be infected after the spreading? I am the source of the spreading, okay? So node I is the source, and then you wanted to predict how many people will be infected after the time goes to infinity, because this is the SIR model. In synchronization, we will assume that this variable is 1 if the oscillator is synchronized and 0 otherwise. So in first case, you have a regression because my output is a real number. And here we have a classification because my output is just a label. Basically, the task is to try to evaluate this function, okay? But this function can be very complicated because, for instance, we have a nonlinear process, we have different patterns of connections, we have feedbacks, so it's a very complicated function. And also here, if you take a look on this small network, for instance, if you remove the red node, we will disconnect all the other nodes. So the observations are not independent, okay? So when I use statistical methods, we will assume that all the observations are independent. In this case, we do not have independent variables, okay, and also observations. Then the solution is to use machine learning, okay? So what we did is to assume that for each node, we have a set of attributes, for instance, degree, clustering, between centrality, page rank, key core, and several other measures, okay? This is my output, can be, for instance, the fraction of infected nodes in the epidemic spreading, or the state of the oscillator. To evaluate this function, we consider the random forest and neural networks, okay? And then we have a training set and a testing set. Then we will have to provide some examples to our learning model. To select these training examples, you use the key-fold cross-validation. The key-fold cross-validation, what to do is to divide the data set in different folds, use one fold for testing and all the other folds for training, okay? Then, by performing this approach, here you can see this. Here you have the data, here you have the prediction, and this is the ideal prediction, is this line. Then you can see that you can get very good prediction for epidemic spreading, okay? So you can see that the prediction is very accurate for epidemic spreading. And also, we can see that by using random forest algorithm, we can quantify the importance of each variable on the dynamical process. For instance, we verify that the key core and degree are the most important variables associated to epidemic process. So if you wanted to control the epidemic process, then we needed to change the key core mainly and also the degree. Okay, with these two variables, we can try to predict, to control the propagation of a given disease. Indeed, this solves the problem of identification of most influential spreaders, because this is a typical problem in network science in which people try to identify which centrality measure is most related to epidemic process, okay? So people consider just one measure at a time to try to perform this analysis. For instance, this paper verified that the key core is the most important one. So in several papers, people suggest that it's between centrality, others suggest that it's the degree. So, but the typical solution is that we do not have just one measure. We have a combination of measures that contribute for the identification of the most influential spreaders, okay? So by using machine learning, we can identify the importance of each measure on the spreading process. So instead of using by just one measure, we can use a combination of them, okay? In the case of synchronization, here we have the Hawk curve. So you can see this is this line gives the random case. For instance, if you just perform a random classification, and you can see that you can get a very good result, a very accurate result for the Kuramoto model. And also we can see that this classification is stable for different couplings. For instance, if you have very small coupling and very large coupling, we have more or less the same accuracy, okay? And also, we can try to identify the most important measures for synchronization. And here you can see that if you change the coupling, the importance of measures will change, okay? So for instance, you can see that for small coupling, the most important one is the key core. So you have local most of the iterations will be local. But if you increase the coupling, we can see that between centrality will be the most important one. So it's a kind of the influence of network properties depending on the coupling. For small coupling, we have a more localized influence. So the key core is the most important because related to the number of neighbors of each node. But if we increase the coupling, we have effect of long-ranging effect. So the betweenness will be the most important, okay? So I can see that machine learning is a very, very useful tool to predict the dynamical process in network. But we have many challenges. For instance, some big challenge is, can you get some useful information from the shape of the function f? For instance, when you use a neural network, we have the adjustment of the weights, and this adjustment gives the function f, but it's really hard to interpret, to try to extract some useful information. So this is a challenge. Another one is, how can we improve the learning process? For instance, if you combine classifiers, if you combine different methods, if you perform some pre-processing, so you have a lot of research to perform in order to improve this learning process. And also, what are the conditions for learning? For instance, if you have a model, can I prove if this model will really learn the dynamical process? So this is a big issue in statistical learning. So you can try to develop some theory to verify what are the conditions for the dynamical process and network structure to have a good prediction. Also, we have temporal networks, multilayer networks, networks with noisy, heterogeneous dynamics. And also, maybe you need to develop a new statistics because here we do not have independent observations and independent variables. Everything is connected. So traditional statistical methods are not useful in this case, okay? So this is what I have to say. Okay, thank you.
Thank you very much.
Okay.
Thank you for this very interesting talk. I have one observation, comment, and some questions.
Yeah.
My observation is, in my opinion, all the machine learning that you applied, you don't apply machine learning to the networks themselves, but to the projection or embedding of the network on Euclidean space, because you transform your networks in a feature. It's a vector of features.
Yeah.
Okay. And then my question is, do you know if with these machine learning techniques, you mentioned that you can modify the parameters you provide and the level of importance for different parameters, but how can you know if you modify, for instance, the two less important parameters can provide probably a better classification than if you modify the most important one?
Okay.
So, and my second question, if I can, is do you know if, for instance, instead of working on the space, on the Euclidean space, after all it's on Euclidean space, do you know if there's any machine learning techniques that you can directly apply to the native space of the network, you know, like wavelets on network or wavelets on manifolds? There's a lot of literature on that, but I don't know if some machine learning techniques have been applied to these manifolds.
Okay, so the first question, for instance, if you wanted to quantify the importance of each measure, so for instance, maybe, I don't know if I really understand, but for instance, when we assume that we are using we're trying to predict this function. Here you have some information that we don't know. Is, for instance, this noise error includes all the information. For instance, maybe there is a very important measure that's not included in your model. But if this parameter will give the error. For instance, if you do not have enough information, this error will be very big. Okay, so this is one way. And the case of manifold, if you have one way to extract some features of your process, your mathematical entity, for instance, you can try, and you have the output. What you can do is try to infer also a learning model in which you can try to learn the evolution of a given dynamical process based on the features you have. I think it's possible.
We have 2 more questions.
Okay.
In the first part of your talk, not this one about prediction, but the first one.
Okay.
Okay, so you commented that your hypothesis led to the conclusion that the most important things for synchronization is the shortest path.
Yeah.
So you say that usually you expect that if you decrease the shortest path, synchronization becomes better.
Yeah.
This is the opposite of what happens. The first paper that studied synchronization in network is called the paradox of heterogeneity.
Yeah.
That exactly shows that if you take Watt-Strogat's model and you put some short links, so you decrease the shortest path, synchronization becomes worst.
Okay.
And this was solved in 2005 by Mario Schatz and myself in Florence by putting some weight. So how can you, make this prediction? How can you conciliate your prediction with the literature?
Yeah. One point here is this is valid for Kuramoto model. Okay. If you have other oscillator, we can have different result. And also here we have considered, for instance, Erdos-Renyi scale-free networks in the small world network only. Okay. So this is conclusion based on our data. If you have other models like with community organization, with associativity, different probability of hue widening, we can get different results. Okay, so this is based on your data. If you have other data set, maybe you have different conclusion. Okay, this is the idea. So when you use machine learning, we assume that we have a data set. This is the solution for this data set. If you have other types of data sets, we have different solution. So this is used to perform prediction and inference based on your problem only. It's not a very general one. Of course, you can try to generalize, but you need to generate a lot of data. This is the point. Okay.
I have a very simple question, I think, probably silly. But anyway, it worries me. You have a system that you may know or may not know the dynamics, okay? But you are trying to predict. On the other hand, it is most probably, in the case of your example, it is that the dynamics is chaotic. So what I want to know is how is it possible for this system, for this method of machine learning to predict something that the Lyapunov exponent tells you that is unpredictable? So.
Yeah, indeed, I think it's possible because, for instance, in that paper published in Physical Letters, they predicted 80 Lyapunov times, okay, the evolution of the process, okay. The problem is when you do not have enough information, for instance, I don't know if my process, I don't know some variables associated to my process, then you need to use unsupervised learning. It's a different approach. In this approach, for instance, you can use data clustering, or you can use, for instance, classification, semi-supervised classification. In this case, for instance, you have information for just one variable, for instance. In the other class, you do not have information. So you have different approaches to use in different problems. In chaotic problems, I think if you have enough information, you have a deterministic process. For a deterministic process, it's possible to prove that a neural network can predict. Okay, the neural network can predict any deterministic process. So I think it's possible. Okay.
Okay, let's thank the speaker again.
Okay, thank you.
The next speaker is José L. Diestra. He will talk about dynamical and topological characterization of symbolic networks of disease outbreak.
Okay, oops, sorry. This,
Yeah.
Okay, thank you very much to the organizers for this kind invitation. The first thing that I would like to do is to apologize because this title is not the title that I sent for the presentation today. Due to some complications, which I think we are all aware, sometimes you are in the end of the preparation of figures of the paper that you want to submit, and suddenly you check the code again because you notice something a little bit odd that you didn't notice before, and then things changed. So you cannot, you will have to verify things from the beginning, and that's what happened with the previous presentation that I wanted to give. So I had to turn into this presentation, which also has a very misleading title referring what I am going to talk about or I'm going to present or what follows to the presentation, because this was also a project that started with this idea, the dynamical characterization and the dynamical and topological characterization of diseases outbreak. We wanted to do that. We wanted to have a time series of diseases. We wanted to know more about diseases. So we had time series, and we wanted to know if evaluating them with some methodology, we could, in a way, in a clear way, discriminate between one disease and the other, or at least between sources of diseases, for example, vector-borne diseases and airborne diseases and other kind of diseases. We could, in a certain way, differentiate them in order to have an interesting tool for this classification. However, this also mutated into what I'm going to present you today. Again, we succeeded in doing that classification, but not as good as we would like. But in the end, we ended up with a set of measures with a methodology that I think that is important. I think that is important in order to gain a little bit more insight into time series, into diseases, and into some other dynamical systems that we could, in which we could apply this methodology. This work is being done in collaboration with Johan Martinez, Javier Buldú, and Mario Chavez, and we've been seeing this with for a while, and it's been a very nice project, and finally it's coming to an end, or it's reaching the end. Okay, so, back, okay, here. So I'm going to start with the methodology. All the motivation and the introduction was what I just said. So I'm going to start with the methodology. What do we do? What is it that we are doing here in this project? We are using symbolic networks, or we are using a time series. We come from a time series, which is in A here. Okay, it doesn't work. In A, we have a sketch of a time series. Then we transform that time series into a symbolic series. See? A set of patterns in B, which are arranged in that particular way, depending on A. And then after we get the patterns of the time series, using a methodology introduced, well, this transformation from A to B is being done using a methodology introduced in 2002 by Madame Pope. Then from, thank you. We also borrow and extended a methodology introduced by Massoyer, in which they transform the patterns into a weighted and directed network, in which each node or each pattern is going to be a node, and the links between the nodes are going to arrive or are going to appear according to the recurrence of one pattern coming after the other one. So in this case, this particular pattern is going to be connected to this one with a certain way that is going to be given according to the number of times these two patterns appear in sequence in the time series. So this is the explanation of what we have, or this is we define symbols considering groups of E consecutive values in time series. So in this case, we choose 3. These 3 symbols for the whole time series is going to give us a maximum number of symbols of E factorial, which is 6. So we end up in this case with 6, with a with a network of 6 nodes, and each symbol is a node of the network, and consecutive symbols will have a link between them. This is the flow of the connections, and also this tells you that the weight of connections is going to be, in this particular case, 1,9 for all, because each link appears just one time, or appears just once. Okay, so once we have the time series and convert it into a succession of symbols and then into a network, we define a set of measures in order to try to understand what's the role of each of these patterns. So in the end, what's the role of each of these nodes into the network that we created, into the directed and weighted network. So the statistical characterization is going to be divided into parts. First one, a global characterization, which is pretty much a standard when you want to characterize a time series using a time series using symbols. So we use the permutation entropy of the whole time series, well, of the whole series of symbols created from the time series, and then we also calculate the statistical complexity of our time series. This is something that has been done in a couple of other, for time series and for symbolic networks, has been done recently for diseases too in a couple of papers that have been published. So the methods that we introduce here, or the measures that we introduce here for our contribution, are based in this local characterization of the nodes that we get in the network from the time series of diseases. So we define in our net or in our system for our project a nodal entropy. That is a local measure of what we call the entropy. That is going to be defined in the usual way. It's going to be defined as the entropy in a node divided by the maximum entropy that you can get in the node. So in this particular case, the nodal entropy is going to have a twofold, an in entropy and an out entropy. The in entropy is going to be calculated with the links that enter that node, because it's a weighted network, also a directed network, and the out entropy is going to take into account the links that leave the node. In a similar way, the nodal complexity, we are going to calculate the complexity of each node using the links that enter the node and also the links that leave the node. We also, with these quantities of nodal entropy and nodal complexity, we define a flux of entropy and complexity, so the amount of complexity and the amount of entropy that a node handles, referring to what enters and what leaves the node. And also we define the amplification of entropy and the amplification of complexity in a node. So again, it's a measure of what's the rate of attenuation, of amplification, if you may call it like that, of entropy and complexity that a node can handle, or going back to the symbols, a particular symbol can handle. Okay, very well. According to this classification of nodes, using the entropy in a node and the complexity and the flux and the amplification, we can classify each node in the network in different ways. So we can see in the network, depending on their values, on their extreme values of these measures that we introduce, we can see in our network what we call generators of entropy or complexity. We can see amplifiers of entropy and or complexity, transmitters, attenuators, and also basins of complexity, in which these basins in particular are nodes that receive entropy or complexity through their links, but they just keep it for themselves. Additionally to this classification, also we wanted, or we introduced another way of trying to characterize the patterns that we obtain from the time series. For example, let me just tell you the story from this side. We defined what we call the fluctuation of a pattern. The fluctuation of a pattern is just how does a given pattern for a given dimension, in this case, the given number of points that we use to build the pattern, how was the increments and how would the points to build the patterns increase and decrease, and how they do that? Or, yeah, what was the measure of the increase and decrease of the patterns? In this particular case, we choose a very simple way of measuring this fluctuation, of what we call fluctuation, which a couple of days ago we realized that there is an even more simpler way to do that, to define the fluctuation, but this one is okay. For example, in this case, given a symbol of size 3, we take one of the symbols, the pattern 0 to 1, that is defined here in this plane, 0, 2, and 1. And then, in order to determine the fluctuation of this pattern, we just calculate the Euclidean distance in this particular plane from this point until this point, which is the order of the pattern is that the first value is the lowest, the second value is the largest, and the third value is the one in the middle. So for this pattern, we calculate the distance, the Euclidean distance from this point until this one. If we define, if we normalize the plane where each step of time is of length 1, then this distance is 1 plus 2 squared. So the Euclidean distance for this whole pattern is going to be given by this one, for 3.665. It's just a distance. It's just an Euclidean distance from this point to this one plus the Euclidean distance from this point to this one. Using this characterization of the fluctuation of the patterns, we ended up for symbols of size 3, we end up with just two types of fluctuations. Fluctuations of patterns which just increase and just decrease, which have the same fluctuation, because the distance from this point until this one is the same from this point till this one. And we end up with fluctuation, what we call the second fluctuation, in which all these patterns have the same Euclidean distance between their points in this plane. So we just end up with two kinds of fluctuation. Okay. These are the measures that we introduce in order to characterize our time series. These are measures that we introduce in order to characterize our diseases, or the diseases that we are working with. So now, where do we apply these methods or these measures that we are coming up with? We tested them, or we wanted to test them to begin with the original idea. We wanted to know if we can discriminate diseases, if we can differentiate diseases using this methodology. So what we did, we picked a set of, in this particular case, 10 diseases. Why these 10 diseases? Because at that moment when we started evaluating, they were the ones that were more complete and more clean and had different dynamical backgrounds. In this case, we are using dengue, we use influenza, and we use malaria. Sadly, this table could not be completed. Why? Because some countries do not report diseases and some others report other diseases. For example, Colombia usually reports dengue and malaria, but has a very low report in influenza. Exactly the same way with Venezuela and with in other diseases. In this particular case, Japan just reported a lot of influenza, but not dengue and malaria. So we ended up with this table in which we wanted to compare our measures and try to see if we could discriminate or we could differentiate different diseases. We have 10 time series, different ranges. These numbers that are here is just the year. We have data from Colombia from January 2005 until December 2016 of dengue and malaria, and this is exactly the same for all the other values that we have for all the other countries and other diseases. This is just a very messy representation of all the time series that we are using, but it's just to be shown. Okay, so we have the data, we have a methodology. What do we do now? We apply this methodology for our diseases. What we have? Okay, we plotted the complexity, the out complexity of a node and the in complexity of a node. So we ended up with a plane of complexities for each of the diseases. Red is dengue, influenza, and malaria. And we ended up with these results. In this particular case, we can see that there is a positive correlations between the complexity that enters and leaves a node. The apparent differences between the diseases that we are using are given to influenza and to malaria, or for malaria. We can differentiate these two diseases very, very well in this particular case, in which we can say that the complexity that nodes of the nodes, or the complexity that manage the nodes in a malaria network in the way that we have built, is the ranges are very low compared with the ones that manages the influenza nodes. This differentiation is due to what I think, that's my interpretation of these results in this particular case, is due to the seasonality of the diseases. The seasonality of the diseases, the seasonality of influenza here is playing an important part. Malaria did not have a seasonality in the data that we use. Now we can ask, okay, but dengue, but why dengue is behaving more like influenza than with dengue, since it's also a vector-borne disease, other mosquito, but still a vector-borne disease? Well, particularly these 3 points that we can see here, these 3 points are due to the time series that comes from Mexico. In this case, Mexico shows a seasonality-like behavior of the dengue disease, which is not shown by Colombia and by Venezuela. So my interpretation of these results is that, yes, definitely, well, for me, or for what I've seen, or from the data that I get, these 3 points, since these 3 points are due to the Mexican data, so it would have to be something with the seasonality of the diseases. Again, same qualitative results we can obtain for the flux of the complexity and the flux of the entropy, but in this particular case, with a negative correlations between the negative correlation between these fluxes. Again, in this case, what we see is that there are some nodes which can handle, or the nodes that handle a lot of entropy, generally handle very low amounts of complexity. One other difference in this case is that influenza and malaria have nodes who maximize their use of the flux of entropy, and also have the lowest value, in this case 0, or do not manage any complexity in their dynamics in the network. Okay. Again, since I am running out of time and still have a couple of figures to show, I would like to show very fast this result. We also plotted the plane of amplitudes, the amplitude of complexity and entropy, and we saw that we could characterize, or we could see in this plane of amplitudes 4 regions that define very well the behavior, or the behavior of each of the nodes that we are seeing in the network. So we can see here nodes who, in this particular place, right here, that there are nodes like this one in dengue, and also here in influenza, nodes who handle very low values of amplitude, or amplify very poorly, or attenuate the entropy, but those nodes that attenuate the entropy also increase the largest the complexity of the network. Things that happen again in Mexico or in dengue and influenza, but doesn't happen in malaria. Again, from my point of view, from the data that I have and from the results that I am obtaining, I would definitely attribute this for the seasonal behavior of the diseases. The last thing that we did was to use this fluctuation that we introduced. So the fluctuations in the end, what does is that reduces the number of different parameters that we are, or different things that we are going to see in the time series. Because if we have a time series of 1,000 points, and then we use d equal 4, or a dimension of 4, in order to create each of our patterns, we are going to end up with 24 different patterns, and those 24 different patterns are going to give us information about the time series. So in this case, we wanted even to reduce a little bit more and see if that reduction, again, give us enough information in order to understand the system that we are working with. So we use the fluctuation, and with the fluctuation, when we use 4 points for the pattern, we have 24 nodes, but if we classify them by the fluctuation, we end up just with six kinds of fluctuations of the patterns that we obtain. So in this particular plot, we are showing the interplay between the entropy and complexity role of the nodes and their centrality in their disease. What do we see here? We group nodes with fluctuation 1, and we calculate the average eigenvector centrality, or their centrality, of those nodes in the network. And we can see here that the behavior between dengue and influenza shows that there are nodes, there are certain patterns that accumulate importance, or are really, really important in the network, and this important place of those nodes in the network implies that the other nodes are going to just live in a very secondary role of the dynamics of the time series that we are studying. That doesn't happen with malaria. In malaria, there is a little bit more homogeneous behavior of the importance of each of the nodes in our networks. We did that also in order to compare our diseases, our real-time series with synthetic time series. In order to compare, we built this same plane of fluctuations and eigenvector centrality. And in this case, we just ended up with the two dynamics that resemble the most the time series that we were using. In this case was an autoregressive model and also a setter model that we could talk about the specifics of these models a little bit later. And here also we show the global position of each time series in the plane of complexity and entropy. We can see that the diseases all kind of gather here. This is influenza, this is dengue, and here, back here, is malaria in the side of negative correlations of complexity and entropy. But what we can see is that in general, or from the global perspective, influenza has a larger complexity than dengue and even than malaria. So just to conclude, many other conclusions that we can introduce here, but just in order to finish and not take more of your time, we introduce in this project 4 novel measures to characterize nodes in a weighted and directed network. This is very important. The important part of this is that we can use these measures not only for diseases. We can introduce it in the characterization of any other time series, things that we are doing at this very moment. We also introduce a quantity called fluctuation of a pattern. Now we are trying to see if this fluctuation of the pattern is going to give us at least the same information as we get when we use the symbolic representation of the network in order to see if this is an important measure that we are introducing. Here we use the time series. We built the plane complexity and entropy, and we see how, well, not really clustered. The diseases do not cluster exactly in very different regions, but we can see some differences which, with long enough time series, where we can see the dynamics in a better way, we could maybe have better results. And then we compare this characterization diseases with time series and with synthetic time series, and we see that, and there are some resemblances that still are to be tested, the exact resemblance of this characterization. And with this, I just finished. Thank you very much for your attention, and well.
Questions?
Show me the last slide there. I mean, the lower line is the line of the
yes.
Random distribution.
Yes.
Yeah. So the point is, what I'm trying to say is so am I to interpret that the distribution of these diseases is completely random? Is that what am I to interpret? I don't know. I mean,
no, what we are seeing, these are average. Yeah, these are averages of the different diseases of the different regions that we use. So in this case, there are 3 regions is the average. But what we are saying is that yes, malaria has a very almost random behavior. Yes, that's what we can say about malaria in this case. Yes, that's what we saw with the data that we had.
Okay, let's thank the speaker again.
Thank you.
So this one should be okay.
Yeah. Okay, esto es aquí.
Ese de Javier.
I don't know why this is not going on to the.
Okay, so
It's a PDF file.
yes.
It's not going on to it.
No, yeah. So for that we do view full screen.
Okay. I generally use PPT.
We'll give you have 5 minutes.
Yeah, thank you.
Have a
I
pointer.
just told it. Okay.
Okay, so the last speaker of this session is Nivedita from University of Delhi. She will talk about spectral and network analysis of financial systems.
Hi. I think everybody's very tired, including me. But I'll be talking, well, I should first thank the organizers for giving me this opportunity to come here and give my talk, in particular Nilima, for encouraging me throughout my life, actually, in education. Yeah. And so today I'll actually talk about, spectral and network analysis of financial systems. And this is done in collaboration with my student and postdoc, Pradeep, who is in Thailand these days. Okay, so the outline of the talk will be the following. I hope I'll reach the end. With a brief introduction to financial markets, I'll go on to describing the system that I'll be studying and the data. And I'll be studying two data sets, global financial indices and the foreign exchange rates. There I'll study the financial correlation metrics, both the cross-correlation metrics, and find out its spectral properties. And I'll do network analysis, which has thresholds in it, and study the properties. My main objective of this work is actually to control the networks that I'll find. In particular, to control the extreme events that we'll have in these systems, which is the crashes and booms. It's not working here. So this is a brief introduction. So financial systems have been considered very highly, and which have highly complex evolving systems with many unknown agents which govern them. And there are many types of financial markets, the stock exchange, the foreign exchange, and so on. And to understand the complex behavior of these financial markets is a great challenge. Okay, so the system that we'll be working on, we were studying, is these two systems. There are 31 financial markets, and we'll be studying the system from 2006 to 2015. And these are the indices that we'll be interested in, the European, Asian, and the American markets. Okay, so this is the European and American, and this is the Asian. This data is taken from Yahoo. And then we'll study another market, which is the foreign exchange market, which has 21 different countries, and it's been taken from the Federal Reserve Bank of St. Louis. And this is the data bank. Okay. Okay, here is a dictionary between the symbols that we use for the countries and the symbols that will be used, and similarly for the currencies. So I'm not going to dwell too much on this. Here we'll process the data, which are coming from the beginning of 2006 to 2015, a period of 10 years. And we'll be doing daily logarithmic returns, defined in this way, where the SI are the prices of the commodity. And T goes over a year, which is 250 days. And the delta T is closing price, the 1 day. Okay, so daily prices. And then the returns will be defined in this following way, where sigma is the standard deviation. Okay. Everybody's familiar with this. But maybe the students will benefit. Okay, so we calculate the correlation, cross-correlation, Pearson's correlation coefficient, which is given in the usual way. And for the two systems that we are considering, the global financial indices and the FX rates, the correlation matrix, the heat map is, for the 10 years, is given in this way. And here is given the distribution of the elements for all these years. Okay? And one notices that it's non-symmetrical, okay, about 0, and there are high positive correlations and a small number of negative correlations. Whereas in the FX rates, it's more symmetrical. Okay? The mean is, of course, a little bit lower than the previous one. And here's the average off-diagonal elements, the sum of the average off-diagonal element. And you can see that 2007, 2008, 2010, and 2011 are high average correlations for the global indices. And they do correspond to the mortgage crisis, the global financial crisis in 2008, and the European sovereign debit crisis. And the exchange rate shows a very different behavior, actually. The high average correlation is in the range 2010 to 11, okay? And that it picks up this European sovereign debit crisis. Okay. Corresponding to the correlation matrix, you can construct a null model, which is formed by shuffling the columns and the rows of the correlation matrix. And that turns out to be random Wishart matrices, whose properties are very well studied, and are given by this distribution, which is the Marchenko-Pasture distribution, okay, where lambda plus and minus are the extreme eigenvalues of this Wishart matrices, which is the randomized version of the correlation matrices that we started off with. Okay. Q is W over N, where W is the length of the time series, that is 250, and N is the number of different different time series that we have. Okay, 31 in the global indices and 21 for the FX rates. Okay, so there's 31 countries in the global indices, and the FX rates, the exchange rates, there's 21. So these extreme bounds of the null model are these numbers. Okay, so the extreme lambda plus is 1.8, and the lower one is this, and FX rates is 1.6 and 0.8. Okay, if you look at the eigenvalues of the real metrics, okay, in this case the global indices for all these 10 years, and there's a complete one and a random one, you see that beyond, that means the outliers, are in 2006, 1, 2, 3, 2007 again 3, and 2008 there's more. That means more number are coming out, and so on. Okay. Whereas if you look at the lower outliers, that is, this is the random case. Okay, so the lower ones will be here. So the lower, that's about 0.8. Okay, so there, 2006 is so many, 2007 is so many, and so on. Okay, the outliers on the lower end. Okay, and you notice for these lower outliers, the numbers that are coming out are many more. Okay, that's one observation. So the outliers, and for the FX rates, we've also done the analysis, and similar results hold. And here's a table in which we've summarized the results. That is, for outliers, in the lower end, the numbers are this. Okay? So the numbers are very high for 2007, 8, 9, 10, 11, okay, and decrease. Okay? In the lower end, on the higher end, on the other hand, did it work? Yeah. It's working. Okay, now here I go back. So now, whereas in the higher end, the number of eigenvalues that are coming out are not very much. Okay, they're just 3, 2, etc. They're almost similar. Okay, here the outliers are increasing in number at the lower end for the extreme periods. That means in the crash periods. Okay, so that's a very important observation. And similarly, for the FX rates, you notice that these numbers, 2008, 9, 10, 11, which are the 12, which are the crash periods, have outliers more in number than the calm period. There is 10, 9, and the calm period 9, 10. Okay? Whereas the extreme eigenvalues on the top end, the top extreme eigenvalues, don't change very much. Okay? So that's an important thing to notice. And here, so that's one result. And one could go on and analyze some other indicators, which is the Shannon entropy of the eigenvectors. Okay, defined in this way. Okay. And we look at the entropy versus the eigenvector components, and we get these graphs for the different years. Okay, the 10 years that we analyze. Okay, the eigenvectors are arranged in an ascending order, and you notice that the smallest eigenvectors have the largest information, okay, and are highly localized. We'll see that in a minute. Whereas the top eigenvectors are not. Okay. Comparatively, the lowest eigenvectors are containing most of the information. And a similar result is there for the global. Okay, this is the global index. Okay, this is the FX rates here. So this is the global index. This is the FX rate. A similar result. And notice this black line is the random shuffled situation. Okay. Now we look at the eigenvectors closely and look at the eigenvectors for the first largest eigenvector, eigenvalue. And this shows that this corresponds to the market mode. And one notices that certain modes, okay, are different from the market modes for the other side. So this is going positive, and this is going negative. Okay, and it turns out that the years 2008, 2012, and 2014, which is on the lower side, are the ones that are corresponding to the crisis. This is from the eigenvectors corresponding to the first eigenvalue. This is the eigenvectors corresponding to the second largest eigenvalue. Here, one can see that if you take a line at 0, that this sector distinguishes two sectors, okay? The ones on top and the ones on the bottom. And so the two sectors are the European and the American sectors, okay? And the Asian and the Pacific sectors, which are these. And it looks like they're based on their geographical location. Okay. We can also take the eigenvectors corresponding to the smallest eigenvalue. Okay. Here, if we draw the square of the eigenvectors, components for the smallest eigenvalue, the components which contribute the most are these, this, and this. Okay? And this is the sector which corresponds to France, Germany, Spain, and the European Union. So they're corresponding together. Okay? And this is actually a result for the full period, 2006 to 15. It's not year-wise. Like it's not the rolling window. And the significance of these four being together is still not known. We're still trying to figure out that. And similarly for the effects. Okay, so we have a cluster of Netherlands, Belgium, France, Germany, Spain, and the European Union. Okay. Here it is. And it turns out that France is the most influential. Okay, this is for the global financial indices. So let's look at the eigenvector analysis for the FX rates. Here, notice this is the eigenvector corresponding to the first eigenvalue. Here it's completely, I mean, all the market modes are not in the same direction, okay, as observed in the global indices. Notice here, this is the eigenvector corresponding to the smallest eigenvector. And it shows that Denmark, European Union form highly closed clusters. Okay? And out here, there is UK, South Korea, Mexico, New Zealand, and so on. And South Korea turns out to be the most influential. Okay? So now let's turn to the network analysis. I'm making the network by a graph with n nodes, which are given by the stocks and the exchange currencies. And where the edges are 1, if the Cij is the correlation matrix is greater than some number theta, which is called the threshold, or 1 or 0 otherwise. Okay. So the different thresholds will give different networks. This is the networks for the full 10-year period, okay, with different threshold. This is with threshold 0.1, 0.3, 0.5, and 0.7. So these are the strongest connecting nodes. And yeah, for the exchange rates, we have a similar. Okay, and these are, of course, the strongest nodes. And here is a graph of the network density versus the threshold for all the periods, for the global indices and the exchange rates. And one can notice that small things like the mortgage price is in 2007, and so on. So I'll just rush through this portion because lots of talks on networks. So this is the average degree for the two systems that we've discussed and the different years. Okay, and this is the average clustering coefficient. And you get some indications, okay, like this and on. Okay, so what I wanted to turn to in the next 5 minutes is the analysis of the indices before, during, before, and after the 2008 crisis. And here it is for the eigenvalues. Okay, and you notice that the largest eigenvalue is at 14. Before the crisis, it's at 12. Here it's at 14, and back to 12 after the crisis. But if you look at the square of the smallest eigenvalue component, you find before the crisis, these France, UK, Eurozone, Netherlands, Switzerland form a sector. During the crisis, on the other hand, France, Germany, USA, Spain, Netherlands, and Eurozone form the cluster. And after the crisis, it changes. But France, Germany, Spain, and the Eurozone. Okay? So it looks like there's more number of countries coming together during the crisis in this, when you look at the smallest eigenvector components. And one can examine also the second largest eigenvectors and so on. So there are different clusters. Here I'm showing you a picture of the networks. This is the one before the crisis. This is the one during the crisis, and this is after the crisis. After, for different thresholds. Okay? So if you go on increasing the threshold, this is the picture. Okay? Now you notice that at the threshold 0.9, these are the nodes which are connected, and actually they correspond to the smallest eigenvector that you calculated using spectral methods. Okay? So I'm sort of done. I wanted to exhibit that we've sort of the smallest what I wanted to make the put the message through that the eigenvectors are very important, and the outliers in the lower end are extremely important in identifying extreme conditions and being a good indicator of when crashes and booms happen. Thank you.
Questions?
Thank you. Thanks, Nivedita, for a nice talk. So, I mean, any of these, let's say, parameters, let's call them, that you calculate, have you seen if they give you any information about a crisis coming? I mean, like for instance, I mean, you took the 2008, yes. that was a well-defined day when it started.
So we're taking the windows. So we've taken windows which a rolling window. Say you're taking a rolling window of 1 year, 250 time daily. What do you call this? The spacing. I mean, the time is 1 day. Okay. So, but 250 days. So you're taking it across. Yeah. Okay. So what you can do actually is go very slowly in the rolling window and look at what's happening, both at the network level and the spectral analysis. And when some of the, for instance, I mentioned the US went away or came in, that caused the crisis. So if you have to go through the rolling window very carefully. And it's not, I mean, I'm not sure how far you can see, when you can see it. Because here I've just taken, I'm not giving you a rolling window scenario, but I think we have enough computation to do that. So if you do that, you can see that, say, for the example, US coming in, and then it's crashing. So there is, what do you call, in the future there is scope in order to find indicators which give you a prediction. Yeah.
Any more questions?
How threshold dependent are your results?
They are very dependent. But the crisis will happen. I mean,
But this result which you said, for example, you said that the crisis was essentially the US coming in and the US going out. That won't change.
yeah, that won't change. That won't change. Yeah, the threshold is just hidden something pushing through. And the problem is that where do you put the threshold in your networks? I remember a talk some young person was giving here. He was putting his threshold arbitrarily, because you don't really. But here's a way to do it in a very precise manner. You go to your lowest eigenvalue. You see the sectors, and you fix your threshold. So there's some way of doing it. Yeah.
Okay, thank you very
Thank
much.
you.
So let's thank all the speakers of this session. We have coffee.
Much needed.
Thank you.
Thank you.
Okay, so yeah, this was missing. So now,
So that was missing.
yes,
I see.
yeah,
I
the
was thinking, why
previous
didn't it?
speaker took it.
Vai dar mais tarde, né?